Okay, in this video I want to actually sweep the Apache Labs software-defined radio systems filters, look at the filter sizes, calculate the shape factor, display them all, look at the average displayed noise floor of the receiver system, and also a birdie in the receiver that is also kind of interesting. So the first thing that I want to do is bring up a little bit of how we're going to actually look at the waveform we're going to be measuring and talk about some of the initial setup that went into the actual part to get here. The view that we're looking at right now is called the spectrum, or just spectrum. It's part of the drop-down selections that anybody has in the main skin of the software. You have Panafall, phase, scope, a lot of different very good tools at your disposal, and this one is called spectrum. So that's the view that we're in. Now some of the initial setup here, if we look at the some of the settings here, let me blow this up so we can see where we're at. This is the test sub-tab, and under the test tab we have several different generators. We have a two-tone generator where we can assign any two frequencies, including making them equal to one frequency for the transmitter. We have a signal generator for the receiver and a signal generator for the transmitter. All very handy and functional. In this test, we're going to be using the signal generator on receive. We have it in sweep mode. We have the level set to 5 dB just to get our gradients matched up here at the relative value. We have the sweep range from 0 to 2500 Hertz, and the sweep rate is 2000 Hertz per second. If we go back to our display tab now, there's also some important things we need to mention here. The FFT is maxed out, which is very important to get an accurate measurement. The bandwidth or resolution bandwidth is minimum. It is 0.732 Hertz, and we're leaving the system window here where it gives a more accurate and conservative value of the actual filters that we're going to be measuring. For this test, I do have the pan adapter selected to average long recursive. However, most times during normal conditions, I would recommend that be left to peak. But this is all for testing the receiver and sweeping the filters. So let's go back to the DSP tab now, and I'm going to pull this down a little bit. Get that out of the way, only what we want to see. Now, this waveform here I generated was just arbitrary. I felt that it would be easy to visualize and fill up the screen in a nice way. And it's a 1000 Hertz filter, 1000 Hertz wide. This is generated by simply tapping your variable 1 tab in your receiver filter combinations anybody has available to them on the main skin. You then have a low and a high, and I just typed in 500 and then the high 1500 for a total of 1000 Hertz wide. And that's what we're seeing here as things generate. Now, going forward now, it's also important to mention that if you look at the lower left-hand corner of the screen, you see some coordinates. Those coordinates are how I came up with these measurements. We'll be using these to calculate bandwidth and the actual amplitude skirt of the filter. Also, we're going to be noting that the 0 dB reference is minus 35 dBm on the analyzer. So that's also important to note. Going forward, our 0 dB reference then for our measurements is actually minus 35. So when we talk about measuring a filter and we talk about a shape factor of a filter, classically I've always measured filters by the -6 and the -60 dB bandwidth points, and then dividing the -60 dB value into the -6 dB value to actually give us a calculated number that can be expressed on how the skirts of the filter actually respond to bandwidth and frequency. So in this case, we're looking at the filter size 1024, as we can see in our tab here, still on our DSP tab. We have several selections ranging from 1024 all the way to 16384, and we'll go ahead and measure these in BH4 and BH7. Because there's a mathematical relationship to the filter size, I'll go ahead and measure one filter, and then I'll cycle through the rest of the filters, and I've already calculated these before the video, and the shape factor simply decreased by 2 every time the filter sizes increase by 2, so it'll cut down a lot on the timing of the video. So to get started here, if you again look at the coordinates down in the lower left, what I want to do here is go 6 dB down initially. Now 6 dB down from minus 35 dB is going to be 41 dB. So I want to go 41 dB down, and I want a crosshair coordinate here to minus 41. Let me get there. I'm doing this by hand. And then I want to take a quick view of what number I landed on. It's about 500 hertz. So that'll be our minus 6 dB measurement. The next measurement will be our minus 60 dB down measurement. And since our 0 dB reference is close to minus 35 dB, that means 60 dB down from that is minus 95 dB. So I'll go ahead and do a crosshair measurement here, get the crosshairs to about minus 95, which is close to there. And the frequency is reading in hertz, which is close to 356. I'll just round that since it's by hand. And the numbers here are a little unusual in the fact in the spectrum mode, the numbers are decreasing as we go left and increasing as we go right on the horizontal plane, because it is measuring how far we are from absolute zero. So even though the numbers are going down, this is actually an indication of measuring the curve of the filter is occupying more bandwidth. So it's 300, I'm just going to say 356 hertz. So the difference then between 500 and 356 is 144 hertz. So we've increased the occupied bandwidth now by 144 hertz looking down the skirt of this particular filter. If we add the 500 hertz initial value to 144 hertz, that puts us at 644 hertz total, which will be our minus 60 dB value. So we're now 644 hertz, which is our minus 60 dB value. We'll divide that into our minus 6 dB value, which is 500. And when we do the calculation, the shape factor comes out to 1.28. And that's the basics of calculating the overall shape factor of any filter, is to reference what the bandwidth is at minus 6 and minus 60. In this case, there was just some extra added calculation and understanding of how the actual numbers relate in the software and the spectrum view here to understand actual bandwidth. So because the shape factor is 1.28, as I increase now to the next filter size, the filter will get twice as sharp, and the shape factor will decrease in half every time we do this. Here's 2048 developing now. It'll be much different. As you can see, now this shape factor, when we calculate the minus 6 to minus 60 dB point, and look at that, the shape factor comes out to 1.14. Now if we go to the next filter size, which is 4096, and follow the same protocol, the minus 6 to minus 60 dB value, we start to see a pretty big increase in the way the filter's looking. The shape factor is getting twice as sharp. Now this shape factor is 1.07. Now if we go to 8192, it will double again, and we will see a measurement that will come out to 1.03, and we'll double that again by increasing the filter size finally to 16,384, and 16,384 will finally give us our maximum and our calculated shape factor of 1.01. Now that looks pretty sharp. So very, very interesting way of calculating the shape factor. They're mathematically proportional to the filter size, and the initial one at 1024 being the most important, and then calculated all of the shape factors ahead of time. So, and we'll display all these on the screen shortly. One interesting thing here while we look at the 16384, over time I've noticed that there's audio in voice A3E or J3E. There's definitely an attribute I don't subscribe to fidelity-wise running these sharper filters. In fact, you can almost hear it in the sweep in the background. It starts to have an unnatural sound. So I would only recommend these higher receive rates for digital communications where intersymbol distortions need to be kept to a minimum, or any kind of digital information needs to be preserved in a way where fidelity really isn't a key thing to the human ear. So it's just an interesting thing to look at. So I'm going to go back to 1024 now, and we're going to switch over to BH7 as this develops. So we're back again, and before we do that, we'll calculate how deep the software is calculating this filter. This filter back at 1024 at BH4, if we reference this, is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and 110 dB. Now this is an interesting measurement as we switch over to BH7, as we're going to see quite a difference here. So 110 dB skirts here with 1024 and BH4 selected. Let's go ahead and look at BH7. Okay, a big difference. All of the ringing has all gone away, and we've increased the filter response curves by another 30 dB almost. So let's calculate this real quick. This is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. This is where the old one was. 120, 130, 140. So this is 140 dB down now by simply going to BH7. Now, some interesting things changed with the shape factor going from BH4 to BH7. Shape factor is a little bit wider here. When we calculated our minus 6 dB point down to our minus 60 dB point, our calculations came up with 1.4. So there was a 1.4 shape factor here as compared to 1.28 with the initial BH4 calculation. Now, I'll go ahead and cycle through the rest of the filters here and then display all the shape factors together. Here comes 2048 at BH7. Again, we're going to be seeing a ×2 increase in the filter size, and every time we do that mathematically, the shape factor also trends in the same direction and decreases in half. So here's a shape factor of 1.2. We'll go to 4096. The shape factor will be 1.1. There it is. And now we'll go to the next one. 8192. 8192 will be 1.05, again decreasing in half. Look at that. I'm going to smush this a little more. And finally, let's go to the last one. 16384. 16384 decreasing in half again. Our shape factor drops to 1.02. Absolutely incredible. Just incredible, and the depth of the filter now within the software is quite impressive. Let me display all the shape factors side by side now. You can now see the overall trend here. As the filter size is starting minimum, we see as the filter sizes double, the shape factor decreases by 2 times every time ultimately, and we can compare BH4 next to BH7. You see initially there is somewhat of a difference, but again, even these minimal filter shape factors are better than an NRAD 8-pole crystal filter ever was. So all of my NRAD crystal filters, 8-pole crystal filters, were 1.6. The 1.6 to 1.5 on my NRAD 8-pole filters. So these are some pretty impressive specs, all calculated by hand using the -6 to -60 dB method and utilizing our crosshairs and the coordinates in the lower left-hand corner. So pretty interesting stuff. Well, the next thing I want to do is look at some of the receiver noise floor characteristics, and we'll go back to the test tab now, and we'll take the sweep and we'll go back to radio, which will turn this off. I'll move this out of the way. Okay, so now what we're seeing here is something a little bit different. We're seeing what the software is interpreting as the average displayed noise floor looking in the spectrum now. And if we use our crosshairs to sort of get a middle ground measurement here of what the software is rendering as the average displayed noise floor, we can see it's reading -167 dB. -167 dB is way beyond the analog counterpart hardware that is put inside this particular receiver, which is an Apache Labs Anon 8000 DLE. So let's look at the actual spectrum now. I'll go to Panafol, and we'll see a little bit different rendering of the actual noise floor. If we take some initial measurements here, we can see the crosshairs I have looking at 192 kilohertz of band at the moment. Our crosshair measurement is -160 dB. This is the actual average displayed noise floor at 192 kilohertz, -160 dB down. Now, if I go to a ×4 zoom, let's see if it changes. So I'm zoomed in quite a bit now, roughly 5 kilohertz plus and minus of center. The average displayed noise floor now, if we look at the cross section, is still about the same, -161 dB. Pretty impressive for an average displayed noise floor. Next, I want to look at a interesting birdie. I'm going to go ahead and zoom out. There's an interesting birdie in the receiver here. Occurs here at 424.5 kilohertz, almost 425 kilohertz, 424.5 roughly. It's an interesting birdie. So interesting to note that as well. I'm going to do some quick rescaling here just to make this look a little bit more normal. Come back down to 3 dB per division here, and this is really about what the birdie amounts to with absolutely no antenna. It's really not much to look at. It tends to have about an S5 signal in the actual peak hold of the S meter, so it's really not much. And remember, if there was an antenna connected, some of this birdie would be covered up too. So it's really not much to talk about on the 8000 here. Well, that's a little bit on the receiver. I hope that some of this was interesting and helpful and what have you. Calculating the shape factors, looking at the actual filter sizes that occur behind the bandwidth curtain. You know, when we talk about the bandwidth curtain is what you see there in the transparent square, if you will. this is our bandwidth curtain here, and so the filter sizes will always have an impact on how we interface with this particular feature. So that's about it for here. I'll go ahead and do some other commissioning videos later on the Apache Labs software-defined radio systems product, and I hope you enjoyed this video. I'm amateur radio operator Tyler, Kilo Alpha 0, Kilo Alpha 73.